Ladies and gentlemen, brothers and sisters in Christ, people of YouTube and beyond, this is part 2 in Connecting the Dots. We're here today to talk about sound, light, vibration, and how everything is connected. In the beginning, there was the Word. The Word was God, and the Word is God. So, from here, we move forward.
Sound. We are a kind of a visually oriented species, though. So I think it would be kind of interesting to hear each of you talk a little bit in turn about why sound is important, and especially, Jamshed, why it would be important in a field like neuroscience, which we think of as a very abstract and, again, kind of visually oriented, looking at scans and things like that. How did you get interested in sound?
Sound is key to communication. Really, even before we were able to read and write, we communicated by sound. Speaking to each other. History was carried along in an oral history, which was very much to do with sound, and with poetics. And animals have sound as well that they use to communicate. So sound is a glue that holds individuals together into groups, because it enables them to communicate, to recognize their species, to court each other, and so on.
And we hear in the womb, we hear in utero before we can see. So
we certainly do.
So is our hearing actually, is it primary to
seeing?
Well,
I would say it's primary, but I would say that by the time you're born, in fact, there is some learning that has gone on, auditory learning. And so an 8-day-old infant, for example, shows a preference for the language of its mother, even if it's spoken by somebody other than the mother, compared to some other language, because those patterns of sound have been heard before.
Wow, as early as 8 days.
Mm-hmm.
Light is a wave of electric and magnetic fields. Sound is a wave of air pressure. According to quantum mechanics, all the particles in the universe have the properties of waves, including all the particles that we ourselves are made from. Therefore, to understand light, sound, and the very nature of reality, it is necessary to first understand waves.
This idea that the universe had some kind of vibration, that everything was somehow in motion. Was he prescient? I mean, has science proven him right in a way?
I think in many ways, yes. I mean, in astronomy, one really tends to think of using sight or perhaps radio waves, but versions of the electromagnetic spectrum. But in fact, out in the universe, pretty much everything is a dilute gas of one form or another, and it's subject to forces, and in response to those, pressure waves, sound waves move. So astronomers routinely now, for example, study sound waves coursing through the sun. The sun actually has many sets of harmonics. You can study its interior that way, but even galaxies have a dilute atmosphere, and there are pressure waves moving through there.
To understand the properties that all waves have in common, consider a wave traveling along a rope. The wave transmits energy and can encode information. Yet each individual atom stays pretty much in the same spot.
Mark, let's talk about the sort of the basic fundamentals of sound.
Yeah, I think we have some visuals. So, Tom, if you bring up the first image here, we have a sort of very, very primitive musical instrument. It's this famous tuning fork. So the metal vibrates back and forth, and you'll notice that next to the metal here are little dots. These are molecules, and this is the atmosphere that we're embedded in. And so each time this moves, you can see it compresses, the molecules get close together. Now, you want to think of this perhaps as a crowd of people, and they are bashing their neighbors. So there's a crowd surge effect. So these molecules bash their neighbors and so on, and there's a propagating pressure wave here where you can see the gas molecules are bunched up, and between there's fewer. So we say these are the compressions, and in between there are the rarefactions. And the waves move to the right. I'm sorry, this isn't actually a movie, but you just want to imagine these moving. And so there's a little bit of terminology here. As these pressure waves move out and ultimately hit your eardrum, the number that hit the eardrum per second is the frequency. And the space between the two peaks here is called the wavelength, and the whole thing propagates along roughly at the speed that the molecules themselves are moving. So the speed of sound is typically the speed with which molecules move. And that's sort of what a pressure wave is. It needn't be the air, it could be water, it could be solids, and so on. And I think it's the big green button, we'll see. Yes, it is. That's good. So there are sort of three aspects to sound. It's worth us just sorting and separating out. So the first would be pitch. And pitch is determined by that frequency. And here sort of is a piano keyboard from the bottom of the piano to the top. And over here are those numbers of waves hitting your ear per second. 30 hertz is the name given to this. 100, 1,000, 3,000. It's a bit of a scrunched scale. And the human range, what your ear responds to, is from a little bit below the bottom of the keyboard, 20 hertz, up to about 20,000 or 20 kilohertz. Here, of course, is the musical staff correctly placed against the notes. And here are two, just to give you that idea. Let's, Tom, if we can just play the top one of these. So that was 600 waves hitting your ear per second. And let's just contrast that with this, 200 waves per second. It's a deeper pitch. So obviously the fewer the cycles per second, the deeper the pitch. That's the first quality of sound. That's frequency is related to pitch. What about volume, loudness? This is a quick sort of graph of a pressure wave here, high pressure, low pressure, high pressure, low pressure. So the loudness is defined by basically how much pressure variation there is compared to the average pressure, but in math terms it's delta P over P. The thing that's really interesting about this is that our ears are amazingly sensitive. So for example, if that range in pressure is 1,000th, not a lot, that's essentially deafening. And on the decibel scale, 135 decibels, that's a jet engine, you're close to the engines. A millionth of a difference in pressure is pretty noisy. That's a party sitting in a party in a crowded bar. And then our ears, very quiet, 15 decibels is a billionth. So I think, as we'll be hearing from Christopher, it's very interesting that the ear is able to amplify such tiny, tiny pressure variations. We have very sensitive ears. And then the final quality of noises, it's timbre, which to use a musical term, or quality, to use the physics term. And that is that nearly all sounds that you hear, including my voice right now, have many, many pitches present, many, many notes. So this is just, here's our frequency scale with low to high. And this is just a particular broad spectrum which sounds like noise. So this spectrum, so loudness up here, for all the different pitches, there's a different loudness. And let's just play this, Tom. So it's just like noise. But of course, music really has a very different quality to our ear. So here's now two spectra of two different instruments. Sorry, something happened there. Let me go back. There we go. So you'll notice that we have two spectra for a clarinet and a flute. So here we have pitch along the bottom. Here's the whole range for a piano, and it goes above that up into the highest notes. And why don't we just play the clarinet now, the top one? So our ears really hear a particular note. And look at the sound spectrum. Here's loudness, and at this point here is a strong spike. Just that tone is present. It's called the fundamental. But then look higher up, all these other spikes. They're called harmonics, and they're what define the particular quality that a clarinet makes. So let's contrast that and play the flute. See, they're playing the same note. They both have this 370 hertz component, but notice how the harmonics are different in the two instruments. That's what makes a flute, and a clarinet. And of course, these harmonics depend on the structure of the instrument. Notice, for example, there's the second harmonic is really present here. It's just absent there. It's quite a difference to do with the way this end is either closed or open. So those are the sort of three qualities that it's nice to keep straight.
But some of it moves us and can have a dramatic impact on our bodies. Shari Edwards knows this. Like a dolphin, she uses sound to reach out with her voice and touch other people.
There's a real hot spot right there. I don't want that.
Shari uses her voice to produce pure tones that she believes resonate within the bodies of those near her and can even help them heal.
And I'm just doing this in my vocal range. We'll go figure out what this sounds
Well, you can feel a vibration in your hand when you make the sound, is that one? Yeah.
I can feel it kind of singing back to me, vibrating back.
Bob Balfour came to her after an accident on his motorcycle.
I went under a truck, and about the front half or 2/3 of my leg was just taken out by something under the truck.
402.
The surgeons were going to cut my leg off, and I told them I played tennis and please don't cut my leg off, and pled with them. I had some of the top orthopedic surgeons in the country that said I would be lucky to walk again.
The surgeons managed to save Bob's leg, but it was still virtually useless 4 years later.
Shari, she did some analyzation with her sound techniques, and actually quite quickly I had improvement in the swelling and the mobility, but over time I've been able to almost run, which I thought I'd never be able to do again.
To excite the beam into longitudinal oscillation, we must shock excite the beam, then input more energy. This is the center of the beam.